Hi, my name is Ming-Ho Lee, and I'm going to be talking about silicon-rich abnormal giants of the Milky Way galaxy. So stars have different chemical makeups, which is the amount that they are of hydrogen, of helium, and of heavier elements like carbon and nitrogen. There are different causes for this. The first would be the enrichment of star-forming clouds, which would be through novas or supernovas, which would introduce heavier elements into those clouds, which would then form stars. The second would be fusion processes, which is throughout a star's lifetime, it'll fuse lighter elements like hydrogen into helium and helium into heavier elements like carbon, nitrogen, and oxygen, which would change its chemical makeup over time. The third would be mass accretion and pollution from a neighbor. So this would be like, for example, in a binary star system, one star accreting matter from another one, which would change its chemical makeup. Observation and identification. So metallicity, or the abundance of the chemicals, would be observed by comparing the spectra of those stars. A star with a higher abundance would have stronger lines of absorption, which could be used to estimate the abundance in that star. And it's shown in this format, which means the log base 10 of the number of whatever element in comparison to another. For this study, the anomalies, they're off the disk. This is chosen because it's easier to observe, and also because stars that are off the disk are less polluted by novas and supernovas. The stars in our study are also metal poor. Silicon richness occurs at many varying levels of metallicity. In this study, we're just looking at the metal poor stars, which would be less polluted and are likely older. Stars that have high carbon abundance are common, and they've been enhanced by mass transfer. So we want that to be low because mass transfer dilutes our study. And silicon richness, the stars specifically looked at are the ones that have abundance of silicon to iron above 3 standard deviations of the data set. This image is the probability density estimate of the stars in the data set. Density contours of the probability are shown as white dotted lines. The black star symbols are the final selection of the silicon-rich stars. The shaded area in the image A are the metallicity range where stars have significant silicon abundance. As we can see from the image, the silicon-rich stars are quite far off from the rest of the data set, the normal distribution of metallicities in the rest of the Milky Way galaxy. So taking from the Gaia DR2 and the Apogee 2 data sets, the study found the proper motion and radial velocities of these specific stars and took distance estimates. And it came out that these stars have fairly large eccentricities. In part A of the image, the shaded region and black dotted region indicate the radius of the Milky Way bulge. Blue line is co-rotation radius. So we can see from the placement of the stars that the orbits are quite strongly off from a normal circular orbit from the bulge. B, the black dotted line is the distance maximum of the thick disk. This is the deviation in z-axis if the plane of the disk is horizontal. So these stars dip quite beyond the thick disk. And C is, with respect to galactic rotation, the black dotted lines separate the prograde orbit, retrograde orbit, and simultaneous prograde retrograde orbit. So these stars vary in their orbits. Some of them are retrograde. What this means is that they don't follow the normal galactic rotation of the spiral arms. This image is of the structure of the galaxy. We can see the galactic bulge, the halo, the spiral disk, the galactic disk, and then globular clusters, which are substructures in the Milky Way galaxy or spiral galaxies, which are gravitationally bound. Explanations of the silicon richness. These could be a new subpopulation of inner halo stars. Their metallicity range allows a possible origin in the thick disk or halo because they don't deviate that far from normal. The silicon abundance could be from neighbor accretion of silicon. And the metallicities and the orbits have other possible origins, though. These stars could have been initially bound and become unbound as a fragmented globular cluster. Globular clusters are, as said before, gravitationally bound clusters. They're formed from the same cloud and thereby started with the same metallicity. Therefore, when we look at globular clusters, they usually have similar metallicities to each other. This would allow explanation of enrichment from unique precursor stars, which would have polluted the cloud, which formed the globular cluster. These are definitely not from dissolved dwarf galaxies. In a separate study, the metallicities of stars from Sagittarius, a nearby dwarf galaxy to the Milky Way, was observed. Galaxies within a galaxy, the metallicities of stars show commonalities, but these metallicities are observationally distinct between galaxies. These silicon-rich stars that we're observing, they match the Milky Way, so they're formed within the Milky Way. Another possible cause is that they're heavily enriched from massive supernova. The silicon richness could be caused by explosive nucleosynthesis of core collapse, which would then form the silicon during the supernova and then pollute nearby clouds. It can also occur in natural fusion of the leakage of the aluminum magnesium fusion to aluminum silicon through proton capture. This would only overtake magnesium fusion at temperatures exceeding 100 millikelvin. The conclusions. Future studies to build upon this study, we would need accurate galactic potential of the inner galaxy to correctly model the dynamics of the halo. Currently, that's not known. Data of more chemical species as well to study natural fusion, accretion, and pollution. Currently, the data set only has abundances for select elements. With more, we can more adequately study abundance trends in the stars, natural fusion rates, and pollution by supernova and such. The significance of this study is that in knowing how these stars got here, we can possibly model the earlier Milky Way structure and its formation over time. That is, if these stars are from dissolved globular clusters. Also, the possible discovery of an abundance formation process from that aluminum magnesium leakage into aluminum silicon, which is rare given the abundance observations in the rest of the Milky Way galaxy. And possible unique enrichment object from a specific galactic epoch. Given the rareness of these stars, it would indicate a unique time in the formation that these precursor stars would have existed and formed the rest of these stars.